in the last lecture we were examining separation of variables in a spherical coordinate system through the example of the effective conductivity of a composite. So, basically what we had was a composite material of some length L, across which we had applied a temperature difference delta T, okay, and this composite material had some spherical inclusions in it. Okay. And if these inclusions, so if you look closely at one particular spherical inclusion, okay. So this is a particle, okay, spherical particle with thermal conductivity Kp, which is different from the matrix conductivity Km. And because of this, there will be the heat flux will be different from the heat flux for a uniform material with just thermal conductivity Km. Okay. So, if you had a simple uniform material, the velocity, the heat flux will be given by Fourier's law, okay, times, I should write this as minus Km, which is just minus Km times T prime. But because you have these particles in there, the heat flux, for example, would, the flux lines would be deformed due to the presence of this particle. They would no longer be straight lines, okay. And because of that, the temperature field will be different from the temperature field in the absence of this inclusion. Example I have given you here is when the particle conductivity is higher than the matrix conductivity. So, in this case we want to find out what is the effective conductivity. If I write the average flux is equal to minus K effective times T prime, where T prime is the applied temperature gradient, okay, delta T by L, where T prime is the applied temperature gradient delta T divided by L. And we were considering this in the dilute, okay, or single particle limit, okay, where the temperature field around this particle, for example, is not affected by the disturbance due to nearby particles. Okay. The particles are sufficiently far apart such that the temperature field is around one particle is not affected by the disturbance to the temperature field around the other particle. This is called the dilute or the single particle limit. This can be, so therefore, this problem reduces to the disturbance to the flux due to the presence of particles in a temperature field which is a linear temperature field far away. Okay. So, we had reduced this to the problem of the, okay, a single particle, okay, placed in a temperature field, okay, which has a linear gradient far away. Okay. So, the temperature field at this location can be written as T is equal to T c plus T prime z far from the particle for r much greater than the particle radius. For r much greater than the particle radius, the temperature is equal to the particle temperature at the particle center plus T prime times z. Okay. And each of these particles it has a radius r, okay, and the temperature gradient is in the z direction. Okay, the temperature gradient is in the z direction. Okay, so this is the z direction. We use a spherical coordinate in the particle reference frame, okay, where we have the 3 orthogonal Cartesian coordinates. Spherical coordinate theta is the azimuthal angle from the z axis, and phi is the angle, the meridional angle of the projection from the x axis. In this particular case, the configuration is axisymmetric. Okay. So, there is no dependence on the phi coordinate. Okay. So, there is no dependence on the phi coordinate. Okay. The inhomogeneous direction we had defined as the r coordinate. Okay. The inhomogeneous direction we had identified as the r coordinate. Okay. Okay. So, the reason is because the boundary condition is that for r going to infinity, okay, t is equal to Tc plus T prime times Z. And I told you that this Tc makes no difference as far as the flux is concerned. The constant temperature does not alter the flux field around the particle, because the flux field is related to the gradient in the temperature. Therefore, this constant temperature does not alter the flux field around the particle. Therefore, we can neglect it in this analysis. Okay. So, for an axisymmetric, del square T is equal to 0 in both the particle and the matrix. So, both the particle temperature del square T is equal to 0, del square T matrix is also equal to 0. Okay. The boundary conditions are this condition for r going to infinity, T is equal to Tc plus T plus T prime times Z. And as I said, we can neglect this Tc, okay, because it does not affect the flux. Okay. And at the surface, we require that the temperatures are equal in both the particle and the matrix, otherwise you will have a discontinuity in the temperature at the surface. Therefore, Tp is equal to Tm. Okay. This is the matrix temperature far from the particle, and you also require that the radial flux, the flux perpendicular to the surface, that is the radial flux, is equal in the particle and the matrix. Otherwise, you will have accumulation of heat at the surface. If the fluxes are not equal, you will have either continuous accumulation of heat at the surface or continuous depletion of heat at the surface. So, if I have minus Kp partial Tp by partial R is equal to minus Km partial Tm by partial R. So, those are the equations and the boundary conditions that we have to solve. Okay. And both of these are axisymmetric, that is, the temperature field does not depend upon the phi coordinate around the axis. It only depends on the temperature in the axial direction, okay, which means the axis, okay, along the axis. So, there is a temperature disturbance only in the r and theta coordinates. There is no contribution to the Laplace equation from the phi coordinate. Okay. So, in the r and theta coordinate, the temperature field is r square d by dr of r square partial t by partial r plus 1 by r square sin theta this is equal to 0 for both the particle and the matrix. Okay. So, this is equal to 0 for both the particle and the matrix. Separation of variables, t is equal to f of r g of theta, okay, t is equal to f of r times g of theta. Substitute into the equation, divide throughout by f and g, substitute into the equation, divide throughout by f and g, and in this case also multiply by r square, okay, because I have this r square in this term here. Okay. So, I have to multiply throughout by r square as well, and I will get 1 over f okay, d by dr of r square df by dr plus 1 over sin theta by d theta of sin theta dg by d theta. Okay, so I should get here one over g, 1 over sin theta d by d theta of sin theta dg by d theta is equal to 0. So, this equation is in variable separable form. This is only a function of theta, this is only a function of r. Both have to be equal to constants that are equal in magnitude and opposite in sign, so that they sum to 0. Okay. Both of them have to be equal to constants, equal in magnitude, opposite in sign, so that they sum to 0. Which one should be negative and which one should be positive? Okay. The inhomogeneous boundary condition is in the r direction. In the theta direction, theta of course goes from 0 to pi, okay, in the spherical coordinate system. Theta goes from 0 to pi, okay, 0 less than or equal to theta less than or equal to pi. Okay. At theta is equal to 0 and theta equals pi in this spherical coordinate system, which correspond to the north pole and the south pole, or the plus z axis and minus z axis, there is no physical boundary. Okay. At theta is equal to 0 and pi, corresponding to the plus z axis and minus z axis, there is no physical boundary. Therefore, any homogeneous boundary condition has to arise from symmetries, as it did at the axis of a cylinder in our cylindrical coordinate system. Okay. Therefore, you would expect, okay, the coefficient to be, the constant to be negative in the theta direction minus alpha, where alpha is a positive number. Okay. Or alternatively, multiplying throughout by g and taking the terms to the left side, I can write this as 1 over sin theta plus alpha g, this is equal to 0. Okay. So, now we had in the last class, you recall, we had made the substitution psi is equal to cos theta, which implies that d psi is equal to minus sin theta d theta, or d theta is equal to minus d psi by sin theta. Okay. Therefore, the equation becomes d by d psi of sin square theta dg by d psi plus alpha times g is equal to 0. And since psi is equal to cos theta, sin square theta is 1 minus psi square. So, in the last class I told you that this is what is called the legendary equation. Okay. Okay. So, this basically is 1 minus psi square d square g by d psi square minus 2 psi dg by d psi plus alpha g is equal to 0. Okay. So, that is the solution, that is the Legendre equation. The solution for this are what are called Legendre polynomials. Okay. So, it turns out that you get solutions that satisfy the boundary conditions in the theta direction only when alpha is equal to n into n plus 1, okay, where n is an integer, okay, where n is an integer. Okay. And the solutions are g is equal to p n of cos theta, where p n is what is called the Legendre polynomial. Recall that in the case of a Cartesian coordinate system, the eigenvalue was I pi. Okay. Okay. We said that in order for the boundary conditions to be satisfied at both boundaries, the eigenvalue has to be either I pi in the scaled coordinates or I pi by L in the unscaled coordinates. Okay. That was because we had homogeneous boundary conditions in that particular direction, okay, where we got the sign functions as the solution. In this case, I will go through and explain how this solution comes about. Okay. The most general solution for G has to be of the form sigma, okay, a n times psi power n. Okay. Some coefficient a n times psi to the nth power, okay, n is equal to 0 to infinity, okay, a n times psi to the nth power. Okay. So, that is, I substitute that into the governing equation for psi, okay, substitute that into this equation, right. Second derivative n into n minus 1, okay, okay, a n psi power n minus 2, that is d square psi by d g square. So, I can expand out this term, okay, I can expand out this term as d square g by d psi square minus psi square d square g by d psi square, okay, minus 2 psi times d g by d psi plus alpha g. Okay. So, we substitute this, okay, I get n into n minus 1 a n psi power n minus 2 minus, okay, the same thing multiplied by psi square, okay, n into n minus 1 a n psi power n, okay, n into n minus 1 into a n times psi power n. Okay. Minus 2 n a n into psi power n minus 1 into psi. Okay. So, I have psi into d g by d psi here, okay, I have psi into d g by d psi here. So, this becomes psi power n minus 1 into psi, which is basically psi power n. Okay. Okay, minus alpha a n psi power n, this is equal to 0. Okay. This over all n is equal to 0. Not, now, look at this equation. Okay. So, first term I have here n into n minus 1 a n psi power n minus 2. Okay. All of the other terms are multiplied by psi power n. Okay. All of the other terms are multiplied by psi power n. Okay. Plus summation of n into n minus 1 minus 2n, okay, n into n minus 1 minus 2n is equal to n square plus n minus 2n, okay, sorry, n into n minus 1 plus 2n, I am sorry. N square plus n minus 2n is equal to minus n square minus n is equal to minus n into n plus 1. Okay. And this alpha should have a positive sign in it. Okay. minus n into n plus 1 a n psi power n plus alpha a n psi power n, this is equal to 0. Okay. In this first term on the left hand side, in this first term on the left hand side, what can be done is to do the summation. So, for n is equal to 0 and n is equal to 1, this term is 0. So, the summation is basically from n is equal to 2 to infinity. For n is equal to 2 to infinity, because for n is equal to 0, n is 0, n is equal to 1, n minus 1 is 0. So, therefore, the summation is basically from 2 to infinity. So, I can, in this first term I can write n prime is equal to n minus 2, which means that n is equal to n prime plus 2. So, the first term becomes summation n prime is equal to 0 to infinity n prime plus 2 into n prime plus 1 a n prime plus 2 psi n prime. Is equal to 0. Since n is an integration in index of integration itself, it does not matter whether I call it as n prime or n. Since both n and n prime are indices for summation. So, both n prime and n are summation indices. You are summing over n prime is equal to 1 to infinity or n is equal to 1 to infinity, does not matter whether you call it n prime or n. So, in the first term I can write this as summation n is equal to 0 to infinity n prime plus n plus 2 into n plus 1 a n plus 2 psi n minus summation n is equal to, I can as well use 0 to infinity, because for n is equal to 0 it is 0 anyway. So, it just adds a 0 n into n plus 1 a n psi power n plus alpha a n psi power n. The alpha should also have a summation in it. This is equal to 0. Now, I have 3 summations with a common factor psi power n. Therefore, I can collect all terms that multiply psi power n. N is equal to 0 to infinity n psi power n into n plus 2 into n plus 1 a n plus 2 minus n into n plus 1 a n plus alpha a n. This is equal to 0. If this summation has to be 0 for any value of psi, if this summation has to be 0 for any value of psi, right, that means that this integrand has to be 0 for each value of psi. Otherwise, if I change psi, the relative weightage of all of those terms changes and you will not get a 0 result. So, if this result has to be true for any value of psi, that means that this underlined term in bracket has to be equal to 0 for each value of psi. This gives us a solution for a n plus 2 is equal to n into n plus 1 minus alpha into a n by n plus 2 into n plus 1. So, this is a recursion relation for a n plus 2 in terms of a n. That means that if you know a 0 and a 1, you can calculate a 2 from a 0, a 3 from a 1 and so on. And those a 0 and a 1 are effectively the integration constants, because I have a second order equation in psi, therefore, I should have two integration constants. Therefore, a 0 and a 1 are effectively the integration constants. Okay. So, this is the recursion relation. Recall that the function g is equal to summation a n psi power n is equal to 0 to infinity. A 0 and a 1 will be specified from the boundary conditions, a 2, a 3 etc. will be determined from this recursion relation for a n plus 2 in terms of a n. Let us examine this recursion relation closely. Okay. For n much larger than 1, okay, a n plus 2 is equal to, okay, I can divide numerator and denominator by n square. Okay, I can divide numerator and denominator by n square. So, I will get divide numerator and denominator by n square, I will get 1 into 1 plus 1 by n minus alpha by n square divided by 1 plus 2 by n into 1 plus 1 by n into a n. Okay. In the limit as n becomes large, you can see that a n plus 2 is approximately equal to a n, okay, because 1 over n goes to 0. In the limit as n becomes large, a n plus 2 is effectively equal to a n. Okay. If a n plus 2 is effectively equal to a n, then this series of a n psi power n at psi is equal to plus or minus 1, okay, psi is equal to plus 1 corresponds to the plus z axis, psi is equal to minus 1 corresponds to the minus z axis. Okay. Then this effectively for large n, okay, a n plus 2 is equal to a n, and I have this a n times psi power n. So, it is basically a sum of coefficients a n. Okay. So, for psi is equal to 1, g is equal to summation of a n, n is equal to 1 to infinity, okay, or 0 to infinity. Since a n plus 2 is approximately equal to a n for psi is equal to 1, this series does not converge. Okay, this series does not converge for because a n n plus 2 is equal to n for psi is equal to 1. Okay. That is what I refer to as the symmetry conditions, the boundary conditions, the boundaries in the theta coordinate are 0 and pi. At these two boundaries, okay, the temperature field has to be finite. Okay. We are finding that for psi is equal to 1, theta is equal to 0, in this series expansion the series does not converge. Okay. So, what do we do? Okay. The only way the series will converge is if for some value of n, okay, this difference, okay, for some value of n, okay, this difference becomes equal to 0. Okay. For some value of n, this difference becomes equal to 0. That will give us the eigenvalues. I will discuss that in the next lecture. How does this condition that the temperature field has to be finite at 0 and pi give us the eigenvalues and the basis functions? That I will continue in the next lecture. I will see you then.